Hi everyone, welcome to DevCon. My name is Bazaliy, and today my talk will be about exploit mitigation techniques on iOS. Can everybody hear me on the left and the right side? Okay, cool. So, yeah, I got it. So a few words about me. I'm from Kyiv, Ukraine. Currently work as a staff security engineer at Lookout. Last few years focused on XGNU, LLVM, and Linux internals. I also co-founded a Fried Apple team, which main goal is to share iOS reverse engineering tools and techniques and methods. So what I'll cover today? First of all, iOS security mechanism, how the iOS security stuff works. Next, quick introduction of function hooking on iOS. I will show techniques that Apple provide to mitigate exploit development and attacks on iOS 8 and 9. And I will show the real exploit that I found on iOS 9 that allowed to run unsigned code. And as a final, we will see how the future attacks on codesign might look like. So what are iOS security mechanisms? So first of all, memory protection that prevent changing executable page permissions, so executable page cannot be writable. And as part of memory protection, we cannot allocate writable and executable regions in the same time. The code signing, which is technique that all executable code must be signed by a trusted party. Sandboxing, like isolating process data from each other and restricting access to files and APIs. Secure boot process, all elements in a boot chain must be signed by Apple. Data protection, which is hardware-based encryption for data at rest, and kernel page protection. So it's a new technique debuted in iOS 9. It's a special patch guard that live in a kernel, live in a IRM trust zone and continuously check for a kernel integrity. So most interesting for us are first two, like memory protection and code signing. I will focus on them today. As I say, memory protections technique to prevent exploit code execution. There is no way for executable page to be writable. There is no way to allocate writable and executable regions in the same time. As a result of that, no dynamic code generation. But starting from iOS 4.3, Apple adds special entitlement that heavily used for allocating JIT pages in Safari JS Nitro Engine. As part of memory protection, non-executable stack and heap, and ISLR in user land and a kernel land. So let's look how they implement it. Here we see vmap enter, which will be in XGNU source code, which will be allocated, we call it all the time when we allocate a new region in a virtual address map. So if region want to be writable and executable, vmap enter just disable vmprot execute flag. The only one exclusion is for entry for GIT. The same stuff for changing existing regions. So if region is executable, is going to be writable, it just will disable executable bit. Again, a special case for use it for GIT flag is set. The next security technique is code signing, which is based on mandatory access control framework. It is a pluggable framework that is permitting new security policies loaded, easy link it in a kernel, loaded at boot time, loaded at runtime, and it's like adds a lot of features to implement new security policies. And code signing is one of these security policies. It's enforced that all code must be signed by a trusted party. In addition, all running code should match with the signed page hashes on load as well as runtime before execution. A few words how the code signature format is look. There is a special, in the Macro file there is a special load command called lc code signature, which points to code signature blob. The key component of a blob is a code directory, which contain version, flags, signer information, and so on. Page hashes, individual stored into slots, and they have started from index 0. There are special data slots for code resources, entitlements, and they have negative indexes. Last is a master hash of all the hashes, called a cd hash, and it usually used to verify ad hoc signatures. Here is a picture how codesign validation and load works in the kernel. So embedded signature got copied to a kernel space, and entire CD hash got verified. No individual page checked yet. We spawn a new process with mark exec v or POSIX spawn, and exec activate image got called in the kernel. It iterates through all the image activators called exec match image act, which handle MAC files and call load MAC file, parse MAC file, load code signature, UBC CS blob add, and finally it call MAC vnode check signature MFI hook. This is how stuff works per page. So page codesign validation works per page fault. Page fault got generated on a page load, and VM fault enter got called. It's called VM page validate CS, which map page to a kernel space. Called VM map validate CS mapped, VM page validate CS mapped, and finally CS validate page, which do the actual comparison between stored page hash and calculated page hash. More details on a page validation. So page fault got generated when the page is loaded, and it's called a VM fault. There are a few states of a page, one called validated, another called tainted. So validated page means that page have a hash in code signature directory. Tainted means that calculated page hash is not equal to a stored page hash. And process with invalid code sign flags will be killed by kernel. A good question, when we need to verify page hashes. So there is a macro, VM fault enter needs CS validation from VM fault. It says that page need to be validation if it's going to be writable, it's belong to a code signed object, it's been mapped to user space, so basically it will be validated any interesting time. A few words how the code sign enforcement works. So Apple uses a special kernel extension called MFI, Apple Mobile File Integrity, which register MFI hook, which register MAC hooks. And like there is a huge set of hooks, just a few examples of them, like MPO vnode check exec, which set flag CS hard and CS kill for a process, which means that process should not allow to load invalid pages and should be killed if it becomes invalid. A big picture how the codesign performance works. So here we have a process in the user land that's called a syscall or a MAC trap. The corresponding sysend, this corresponding function from a sysend got called. It calls out to a MAC framework, which check is there any policy modules requested to hook particular functionality. Next, we call for MFI, which check for a code signature. If the code signature type is ad hoc, we are looking for CD hash at kernel trust hash. If it's not ad hoc, we send out to MFID, which is in user land, which use libmis.lib to validate the CMS blob. So a great question, why we need all this info, right? Before going to problem statement, a few words about the function hooking. So I use function hooking a lot in my work for adding new security features, such as data at rest encryption by hooking low-level open, close, write functions. It's really useful for debugging third-party code, logging and tracing API calls, even could be used for code deobfuscation. All this time I was using industry known method called interposing. This is how it works. So starting from iOS 10, Snow Leopard, Apple decided to implement a special segment in Mac of files for special for dynamic linker usage. The segment calls link edit. It consists information about process of linking and binding symbols during dynamic linkage. It relies on a special load command called deal.dinfo, which serves as table of content for link edit. And here what we can see link edit. Rebase info, which contain rebasing opcodes, bind info, opcodes required for import symbols, lazy bind info, weak bind info, simple bind info for lazy and weak symbols correspondingly, and export info. There is a great article about how it works by Jonathan Levine website, so if you're interested, please take a look. So as I say, it uses special opcodes. Here it looks like. These opcodes are used by DLD stub binder function during dynamic linkage. And we can reuse this information and update bind addresses to point to our functions. So basically, we can intercept and hook functions. This is how interposing works. A few words about DLD shared cache. So what is it? Starting from iOS 3.1, Apple moved all the frameworks and libraries to one big file called the shared cache. It removed all the original files from disk. And I think they use it for performance and security reasons. It's going load to each process space. It's have an ISLR slide which is randomized per device reboot. Previously, in iOS 8, Apple used special bind stubs in DLD shared cache. So basically, during dynamic linkage, the stub address will be updated. But starting from iOS 9, they start to pre-calculate function offsets just inside the hash. So the bind stub is not using anymore. And it was a really big problem for me. So basically, interposing is not working. All the offsets are hard-coded, and I saw what we can do with that, because our product heavily rely on a function hooking. So I thought maybe we can use trampolines. As you remember, there is a technique to hook a functions, which based on direct memory override. So here's an example. We want to hook the function A. We override first few instructions of function A with the jump to function B and redirect the execution vector. In a case, if you want to skip a hook, we can save the original stolen instruction in allocated memory, execute them first, and then jump to a point in function A that executed just after jump. So basically, we reconstruct all function A instructions and execute it without a hook. So yeah, trampolines may work, but as we remember, there are memory protections on iOS that not allow you to change memory regions. So for write to trampoline, the region should be writable, and how we can change the executable region to be writable. Well, even if you can do that, how to switch it back to be executable. And the main question, there is a codesign check on a page load, how we can bypass it. So I start playing with memory allocations and have an idea. What if we can allocate a new memory region with readable, writable permissions just on the same address where the executable region is? So long story short, we can use mmap with map anon, map private, and map fixed flags, overwrite executable region with readable, writable, copy original content back, and yeah, we get a writable memory. How we can switch it back to be executable? Well, that's easy. As it's our memory, it's anon memory, we can use just mprotect syscall for that. And sounds like a plan. We can take a function pointer, get a page address when the function is located, copy original page content to some temporary buffer, and map new readable, writable page over, copy original content back, write a trampoline, switch it to be executable, and we got killed by codesign. So codesign is still a problem. Is there any ways to bypass it? Well, I start playing with codesign implementation in XNU. As you remember, page hash got checked on a page fault. So I have an idea. What if we can prevent a page fault? Maybe we can prevent a codesign check. I found API like mlog. So if you lock in a page, it will be not triggered for a page fault, and there is no codesign check. Here is how full attack looks like. We get a function pointer, get page base, copy page content to a temp buffer, allocate a new readable write page over the original one, copy page content back, lock in a page, write in a trampoline code, and protection page to be executable. So it completely solved my problem with the function hooking, and even this technique was used later in public YALO jailbreak. But I want to go deeper. So I started playing with a dynamic linker. As you remember, dynamic linker is a part of a process, and it's responsible for mapping segments in a memory, loading code signature blob from disk, and even forcing the kernel to do the actual code sign check. It relies on fcntl syscall for loading code signatures. So if we can overwrite or hook fcntl, we can prevent code signature load from disk. The next interesting guy is xmap. Dynamic linker use it as a wrapper for xmap for mapping the segments. So idea is if we can hook xmap and lock mlock all the executable regions during the mapping, we can prevent the codesign check. This is basically how CS bypass was born. We hook fcntl and return -1 to prevent code signature loading. The next is we hook in xmap, lock all the regions that have executable permissions, and there is just step number 3, DL open unsigned code. This technique was open sourced by a guy, Luca Todesco, and is available on the GitHub, so you can check it. Now it's demo time. So I have a few apps here. First, checking how this exploit works. Let's start from one called unsigned code. So what we have inside unsigned code folder? M file and actually a makefile. The M file is just a simple program that dump in a log I'm unsigned code, running in your computer, patching your byte, and terminate the process. Here is how the makefile look like. As we see, there is no codesign step in a makefile. We can build it and try to run on our non-jailbreaking device. To prove that there is no codesign on a file, I use an O tool and looking for LC code signature. As you see, it's not found. So it should dump unsigned code running on your computers. For testing that, I have an iPad mini, which is non-jailbroken 9.2.1, which have a CS bypass loader here that use mlock exploit and continuously check for shared documents folder for any Mac files and execute them. So what I'm gonna do, I'm uploading my unsigned code to a shared folder and run iDevice syslog to get the nslog dump. There's a bunch of logs. So yeah, if you run CS bypass, it will DL open the unsigned code. Yeah, the process got terminated because we returned 0, but we have in syslog unsigned code running your computers, patching your bytes. The next example is more interesting. It's called the Flappy Bird. It is a game that was pulled from App Store a few years ago. I have my copy. I decrypt it and remove the code sign from a file, and I'm gonna install it on non-jailbroken iPad. Again, to prove it's not signed, I use the O tool and check for LC code signature. Yep, there is no code signature here. So the next step is upload to shared documents to a device. And we're running CS bypass. Oh, we get a Flappy Bird game. So it's fully functional as the original one. Yeah, I'm not that good at Flappy Bird, and we are running out of time, so I will switch to the next slide. As a final words, I want to tell how the future codesign attacks may look like. First of all, the hide executable segment. So it is idea based on overlapping executable segment with non-executable, so we basically hide it from a kernel, that this stuff is not executable. This attack was heavily used by TG and Pengu jailbreaks, but looks like starting from iOS 9, Apple really hardened it in DLD, so I haven't seen any attacks anymore. Next one is the hook DLD functions. It's the same attack that I just showed you with CS bypass, so if we can hook or redirect dynamic linker function, we can control how the dynamic linker map a segments. We can hide a segment from a codesign check. And last but not least, hook or update libmiss function. So libmiss is a helper in the user land, which help MFID to check a CMS blob, check provision profiles, and so on. If you can update or hook the functions, we can win a codesign bottle in the user land. This technique was heavily used by Evasion 7 and Pengu 9 jailbreaks. Yeah, I think we're just in time. So if you get questions, catch me downstairs or follow me on Twitter. Yeah, I think that's all. Thank you.